Okay, ladies and gentlemen, here's the last set of notes for the gas laws. We're going through KMT, which is kinetic molecular theory, ideal versus real gases, Graham's law, and the van der Waal equation. First of all, you have to raise your right hand. I solemnly swear.
I solemnly swear
to believe the tenets of the kinetic molecular theory that outline ideal gas behavior, even though there's no such thing as an ideal gas. Okay, thank you.
Wait,
All right.
How did they know? That's like Plato's theory of forms.
Well, we'll leave that right alone and continue
That's what I
on.
was about to say.
Kinetic molecular theory of gas is something I know about. Okay, the kinetic theory, molecular theory of gases are the defining principles by which you can have the gas laws. So you have to believe these tenets in order to get the gas laws to work. Because the gas laws are all in a perfect world, and we don't live in a perfect world. Now this part is actually true. All particles of a gas are in constant, random, straight line motion. That's what this comma was there. So you could write in straight line.
Does that mean like if they bounce off something at a certain angle?
Yes. There's an angle of incidence and an angle of reflection. All collisions between particles are perfectly elastic. You've taken physics, or you're taking physics now, right? I don't think you've gotten to elastic collisions yet, have you? No. Okay. The momentum going into the collision is the same as the momentum going out of the collision. In real life, that's not exactly true, but we're going to pretend it is. Now, the volume of the particles in a gas is negligible. That is saying that the particle itself has a volume of that compared to its container. Let's say the container is as big as this piece of paper. So what they're saying is the space occupied by the gas can be ignored. Now the average kinetic energy of the molecules is its Kelvin temperature. Okay, kinetic energy is equal to 1/2 mv squared, where m stands for, and v stands for velocity. Velocity. Okay. So, the average kinetic energy for our purposes is the same as the temperature. Please note that I have said the average kinetic energy of the molecules is its temperature. If you had two gases, here's one, it's in a gas container. That could possibly be a balloon. Okay, both of these are at STP. The average kinetic energy of the gases, no matter what the gases are, have the same, because at the same temperature, they have the same average kinetic energy. Let's say this gas, A, has a molar mass of 32 grams per mole. Let's see, this gas, B, has a molar mass of 2 grams per mole. If they have the same temperature, they have the same kinetic energy. However, they have different masses, is that correct?
Yes.
Okay. Are their velocities the same? No. No, not at all. Which one would have a greater velocity, A or B, at the same temperature? B, because it's low mass, goes fast. Okay? Low mass, goes fast.
Wait, that doesn't make sense. Wouldn't it just accelerate faster, but the velocity would be bigger?
Nope.
No?
No, wait, no, yes, the velocity of B is greater than the velocity of A. In order, because if they have the same temperature, by definition, they have the same kinetic energy. So kinetic energy here equals kinetic energy here.
Like they did the thing where like they did like Mythbusters is a thing where they had like a real size car go against like a toy car, except the toy car went like.
This is gas.
Okay, gas.
So these postulates are the reason why the gas law works. Boil. When the volume is decreased, the particles are squeezed together and they have a greater opportunity to collide with the walls of the container, creating pressure. Okay, we need to take a little aside here. Pressure is equal to the force over an area. The force is the force of the collisions, and the area is the container. Okay, so you can see if you make the numerator larger, the pressure gets larger, yeah? More collisions makes more pressure. So when the volume is decreased, there is less place for the particles to influence their container, and so you have a greater pressure. Now, when we're talking about collisions, I'm talking collisions with the container, not collisions between particles. They don't make pressure. The collisions against the container. Charles' law, when the temperature is increased, the particles move with a greater velocity because the KE is increased. So they collide with the walls more frequently and with more force. Remember, this works because you're keeping pressure constant. Gay-Lussac's, when the temperature increases, the particles are moving faster. They hit the container more often with more force, therefore they increase the pressure. All right, this is the first time, okay, temperature is the average kinetic energy of the particles of a gas in a sample. Therefore, some are moving faster than others. This is the Maxwell-Boltzmann curve. It is important because the AP folks really like to hear you talk about the Maxwell-Boltzmann curve. You sound really smart. Okay, here's what we're looking at here. Here's a temperature of 273 K, 1273 K, and 2273 K. Here's the velocity of the particles. This is the number of those particles with a given velocity. So at 273, most of the particles have a very small bell curve velocity. As you increase the temperature, the bell curve flattens out more. So the shift of the curve is to the right. More particles have a greater velocity. Do you get that? Oops, wrong way. There we go. Now, root mean square velocity. This is you trying to figure out the average velocity of the particles in a sample at a certain temperature. Here we go. This is the average velocity. So the root mean square, this thing, is equal to 3, that's the number, times R. This is a different gas law constant. Please circle this right now. This is the big boy gas law constant that has to do with energy, joules per K per mole, where temperature has to be in, and FW stands for the molar mass in kilogram. Go ahead and circle that as well, because I guarantee you're going to get it wrong on the test. And you circled it. If you have a highlighter, use it. There's a reason, if we derived this equation, there's a reason that these units must be in this, these terms. We don't need to know that right this moment in time, so you know what? I'm all in favor of we don't need to know it this moment in time. Look, I'm going to draw this highlight. Then maybe I'll make this for this one. All right, calculate the root mean square velocity for the atoms in a sample of helium gas at 25 degrees C. So our formula is the root mean square is equal to 3 times R, the big boy R, 8.315, times the temperature in Kelvin. Do you know this temperature in Kelvin off the top of your head?
273.
298 K. Over the formula weight in kilograms. What's the formula weight of helium gas, the molar mass of helium gas in grams? 4 grams is equivalent to 0.004 kilograms, yes? Do some math. How big is a football field?
100 yards.
100 yards, so a football field is 100 yards, which is approximately 100 meters. Okay.
It's like
So the root mean speed, the root mean square velocity of these helium particles, that means the average movement of these helium particles is 1,360 meters in 1 second. So 1,360 meters in 1 second. Wow. That's pretty fast, isn't it? Some of you can get to the parking lot after school that fast. Okay, moving on to diffusion and effusion. Moving?
So is it U and then a subscript RMS?
Yeah, it's actually mu, but U is a lot easier to format. Okay. Ladies and gentlemen, diffusion is the mixing of gases. How many of you lucky folk have a bedroom on the second floor of your house? How many of you lucky folk have a parent who occasionally makes pancakes for breakfast? Occasionally. Okay, once counts. Oh, all right. How many of you people attempt to sleep until 1 or 2 p.m. on Saturday? Okay, ladies and gentlemen, I remember this from my own high school career. I can remember laying in bed, looking at the clock and thinking, it's 10 a.m. on Saturday, still sleeping. And then about 11:30, 12 o'clock, I smell pancake gas. There is pancake gas that has diffused into my sleeping area from the kitchen. I am going to go downstairs and enjoy a fluffy stack of pancakes because I, even back then, was a really good science student, and I knew if you took the pancakes and you poured syrup on it and then put it in a microwave for like 30 seconds, all of the syrup would squish into the pancakes, and you could put more syrup on the pancakes and it would absorb right in. And so when you cut into the pancakes, you had a great deal of syrup per pancake. Only to make my way to the kitchen and find it empty. Why? Because that pancake gas had been generated at 8:30 a.m. and it took that long for the diffusion of pancake gas to reach my nostrils in my sleeping area. Now, pancake gas has a very large molar mass.
Is there such a thing as pancake gas?
And actually anything that you smell
is a gas.
is gas.
Particles, I thought.
Yeah. All right, so I'm going to say that the pancake mass is enormous. It gets 3 upper arrows. Okay, when I was teaching IPC, I taught it 7th period, and freshman athletics was 6th period, and there was a kid who refused to shower after athletics. Instead, he let Axe body spray do the work for him.
He must have
I
smelled delicious.
swear, this kid would like, I'm in my mind, I'm thinking to myself, here's this kid, 6th period. Ready to go. And I made this kid, I'm not lying to you, sit in the corner. And I thought from way over there. And it wouldn't be 5 minutes until I'm talking away, but all of a sudden it would be Axe body spray, and you can taste it. Axe body spray has a very low molar mass. So, ladies and gentlemen, based on these 2 anecdotal stories, you know that it has great mass, it moves slowly. It has low mass, it hauls
Mass.
Okay, low mass goes faster. Now, the rate of effusion is connected to the rate of diffusion in that the effusion is taking a chamber, putting some gas in one side of it, poking a hole in the chamber, and seeing how fast this gets to that. Not nearly as fun as pancake mass or Axe body spray, but it is a scientific way to figure out effusion. All right. Here is the science explanation. The rates of effusion of 2 gases are inversely proportional to the square roots of their molar masses at the same temperature and pressure. Oh. Okay, really? Low mass hauls blank. Calculate the ratio of the effusion rates of hydrogen gas and uranium hexafluoride gas, gas used in the enrichment process to produce fuel for nuclear reactors. No, you can't have any. No, I can't have any.
We can make some.
Not even. Not enriching anything these days. So, here is the way we do
Just
this.
make some ammonia and bleach and then you get
The rate of one gas over the rate of the second gas is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. Hey, did you see they flipped? Got it? They flipped. They flipped! Exclamation point. All right, so we better have the molar mass of both of these. The molar mass of hydrogen is 2 because it's diatomic. The molar mass of uranium hexafluoride, big number, 352 grams. Okay, you know what? I'm not going to drive myself insane. I'm going to go ahead and set this up so this comes out nicely. I'm going to put this number here, the big number, on top. 352, so that's got to be the uranium hexafluoride. This number here, the H2, take the square root of that. So then this has to go the rate of, okay, and this has to go up there. All right. Now, this is the way, you know what, would you yell at them for me? I'm busy.
Yeah.
Okay.
Do you have to change it in kilograms?
Nope, this one you do not. That was an excellent, excellent question. Write yourself a little note. You do not have to change it to kilograms. However, you would be correct. Your ratio would still be the same if you did so. Okay. this is the way you think about this and solve this. I'm asking you, what is the rate of hydrogen compared to the rate of uranium hexafluoride? When you resolve this, the number is 13.2. So what that's saying is the rate of hydrogen gas is 13.2 times higher than the rate of uranium hexafluoride. Get it? Okay.
I get it.
Now, if you had flipped those the other way around, you would be saying the rate of uranium hexafluoride is compared to hydrogen. The rate of effusion of a particular gas was measured to be found 24 milliliters per minute. Under the same conditions, the rate of effusion of pure methane is 47.8 milliliters per minute. What's the molar mass of the unknown gas? Oh dear.
Wait, so,
Oh, dear.
when you measure rate of effusion, is that the same formula for rate of diffusion?
Yes, it is.
Okay, cool.
That's a good question. So the rate of one gas compared to the rate of another. I'm going to say the rate of the unknown compared to the rate of methane is equal to the molar mass of methane over the molar mass of the unknown. I flipped. Do we know the molar mass of methane?
Yes.
Do we know the molar mass of the unknown? Now, do we know the rate of the unknown?
Yes.
24. Do we know the molar mass of methane? Okay. Okay. In 1 minute, the unknown will diffuse 24 milliliters of it will effuse through this little box. In 1 minute, 47.8 milliliters will diffuse through this little box. Right this moment in time, tell me which, if the molar mass of the unknown is greater than or less than. In 1 minute, 24 milliliters of this effused. In 1 minute,
So it would be
24
32.
of this.
It's sulfur.
Okay. So which one is tinier, CH4 or the unknown? CH4 is smaller, so the molar mass of the unknown better be greater. Okay, I am just really disturbed by this whole thing, so I'm going to write 24 over 47.8 is equal to the square root of 16 over x. I hate square roots.
Square both sides.
So I will square both sides. Then I'm really good. Math, 0.252 is equal to 16 over x. X is equal to 63.5 grams per mole. Does that check out? Are we still doing this to get to this? Does this make sense? Yes. We decided that the unknown had to be a more massive molecule than the CH4, and our answer says that. Okay, I've tried to do this a million times. It never works out for me. It's really terrible. The last time Miss B and I had the concentration of ammonia and the concentration of HCl so high to get these two to move in a tube together that I thought we were both going to kill each other. So we decided you two could do this. All right, so mocking me. This is a Graham's Law experience. In fact, this whole thing, low mass halls, is Graham's Law. Okay, Graham's Law. All right, now, ladies and gentlemen, here we go. Let's talk about real and ideal gases. As you swore an oath to remember at the beginning of this lecture, there are no such thing as an ideal
Would
gas.
a noble gas be ideal?
No, no gas is ideal. All gases are real. They exist on our planet doing the things that we know they're going to do. We can manipulate real gases to get them to conform more like ideal behavior. And what we do is attempt to make the real gases not interact with other particles. Are you getting that? To make them ideal, we want them to be totally non-reactive. So we're going to mess with things like this. Now, let's think about this. You are going down, you are particles of gas. Yeah? Right? All of you. Name the gas you'd like to be.
Argon.
Argon it is. Heard that first. Argon it is. Lovely, lovely
Maybe a
color.
logan instead.
Okay, now, your particles need not to interact with each other. Got it? Not to interact with each other. If I increased the volume of this classroom, would you be more or less likely to interact? Less. You'd have a lot more room in order to rock it around in random straight line motion. So you want the volume to be very high. Now, let's say I increase the pressure in this room. I increase the pressure in this room by taking a giant piston and pushing down on the classroom.
Low pressure.
Okay.
Good.
Would you interact more? So you want the pressure to be high or low? Low. You want the pressure to be low. Okay. Now, let's say, this one's easy. Do I want the temperature to be high or low?
Low.
Even slower.
It's high. This is why. Let's say I take you, okay, here's the scenario. I messed up and I put on Elmo the entire key for the Chapter 5 test. I wasn't paying attention. I'm kind of getting up there in years. I didn't know the key's out there, and you wrote down the entire key for the Chapter 5 test. I send you out to Main Street, and you want to tell your friends. Got it? Now, you need to stop and interact with your friends on Main Street in order to tell them what answers 1 through 10 are, right? Okay. Now, if you were high temperature, you would also be high velocity. You would be high velocity. Would you have time as you passed your friends in the hall to tell them, number 3 is B, number 4 is C, number 5 is A? I don't even know what the answer to 6 was, but there you go. No, you would not. The faster you're moving, the less likely you are to interact. So the temperature should be high.
Wait, that doesn't make any sense.
Yes, it does. Faster you go, the less time you have to interact. The less.
Yeah, but there are more times your passengers are bouncing and crossing paths more frequently.
Okay, ladies and gentlemen, let's say you are not argon gas in this class. You are now elephant gas. Each one of the particles is the size of an elephant. Are you going to interact? Yeah, so you want the molar mass to be small. You want a very low molar mass. One more thing, and here it is. Yes. You want it to be polar or non-polar? Non-polar. Okay, and that just makes sense, doesn't it? This is very attractive. That's why water is water. Very attractive. You want it to be non-polar. Okay, this is the van der Waals equation. This corrects for real gases when we want them to behave ideally. You can see somewhere in here, NERT, the ideal gas law equation. And here is the correction for when things aren't being good. This corrects for the pressure, this corrects from the volume, and you know what? That's all you need to know. Yay. And you don't have to know, you know what? I could make you slog through the algebra here, but it hasn't been on an AP exam since like 1972. We're gonna go that it won't be on this year's.